So in this video, we're going to look back at the optimal binary search tree algorithm and turn it from a backtracking algorithm into a full dynamic programming algorithm. So if you recall, the recurrence we came up with last time was this one right here. And it was built off of the idea that we need to recurse on the left side and create some subtree to optimize the frequencies, and then separately do the right side, and the root is going to be accessed every single time. And so its cost is outside. So the goal here is to decide on the optimal root. Pick an optimal root, and then recursively make the subtrees. Then recursively build subtrees. Okay, so that was the idea behind the recurrence. Now we're going to focus just on, given this recurrence, how can we DPify it? So the first thing we're going to do is we have this sum here. And in particular, that sum goes from I up to k, so it could take up to O of n time to compute. And so we want to maybe try to speed this up over time. So just as we did with the line spacing algorithm, we can actually use dp to compute the sum. So we're just going to have this f right here actually store the sum from j equals 1 to k of f of j. So f of ik is exactly just that sum, and so we can define it recursively as just f of I if there's only one thing. So the sum of a single element is just the element. Otherwise, it's the sum of all the previous elements, which is I through k minus 1, plus the last element. So just as we did before, we can use dp to compute the sum and throw it in a table. Then after we've done that, we can kill that sum and just put f of ik, which will take constant time to call inside this subproblem. So overall, it takes O of n squared to fill up this f table, but after we've done that, we can access the sums for free inside opcost. All right, so the idea here is you can use dp inside dp, and you might even have multiple uses of dp inside dp. So now we have this new recurrence with the fik. Now, how can we dpify this thing? Well, just as normal, we're going to have to look at our subproblems. So how many subproblems are there? Well, I can take any value from 1 to n, k can take any value from 1 to n. So including the base cases, we have I is between 1 and n plus 1, and k is between 0 and n. So in total, there's O of n squared of them. So now that we have our subproblems, what kind of structure should we use? Well, we just have to keep track of an I and a k. So we can do this with just a simple 2D array. We'll call it m, 1 through n plus 1, and 0 through n, so that m of ik can successfully store opt cost of ik. So now that we have our data structure and the subproblems, we can look at the dependencies. So where are the dependencies? This is where we need to draw our graph. So in particular, the ik entry, before we can compute it, we first need to compute the ir minus 1 entry and r plus 1k entry for every r between I and k. So if we think of this pictorially, what is ir minus 1 really? Well, let's draw a little picture. So let's say I denotes the rows, goes to n plus 1 and starts at 1, and then k starts at 0 and goes to n. So we look at a specific entry in here, I comma k. We have I starts, we fix the row at I, and we're moving our column from I up to k. So in particular, the column will always be smaller than k, so that R value can never be larger than k. But the I is the same, so we're always in the same row, but we're changing the R value. So if we just continued this process, we'd look at some arbitrary I comma R, where R is smaller than k. So essentially, we need all of these things to the left of ik. And similarly, here k is fixed, so the column is fixed, but the row is always going to be larger than I. So if we fix our row and just vary the column, we fix the column and vary our row, we'll get I plus 1, k, and then eventually some arbitrary R comma k, where R is bigger than I. And technically there's going to be other ones on the diagonals as well, so this is kind of forming some kind of triangle thing overall. And so that forms the dependency graph. Each of these are needed before we can compute I and k. So what's a good evaluation order? Well, as long as we do anything to where the left, the same row, but everything to the left is present, and the same column, but everything under is present, will be good. So in particular, if we had I, say, go up, starting from n, and then we had k go from left to right, so this will be a single arrow because it's the inner loop. If we do it like this, then we'll always guarantee that ik is processed after all the things it depends on. Everything to the left is covered by definition of the order, and then everything below is covered by the other loop. So that would be the eval order. Okay. Now, what's the running time? Well, we have this min here over all possible R. So because there's n squared subproblems and we're going to have to do O of n work to compute that min over all possible R, we're going to get O of n cubed for O of n squared subproblems, each one taking, in the worst case, O of n. So that's runtime. Now for space, we only need O of n squared, because if we do just the simplest thing possible, we're just saving the whole 2D array. So that's the entire problem. Now there's other evaluation orders you could actually do, so I just want to show you some of those. So here's our dependency graph again. And now we can use all these different eval orders. So the one we described is this one, where I is going up and J is going to the right. But we could also switch the order of the loops, that now I is the inner loop and J is the outer loop. Or we could even do it in this kind of diagonal order, because a diagonal would guarantee that the thing to the left of ik and the thing to the right, or right under ik, is always computed first. Now this one's more complicated, so you probably wouldn't really want to do this, but in terms of a visual solution, that's also a valid order you could do.